Yeah.
So let's begin. I'm Dan Freed, director of the CMSA. It's my pleasure to welcome you here to the first of this academic year's CMSA Tsinghua Math Science Literature Lectures. This is a series that was initiated by St. Yao several years ago at CMSA, and it continues now as a joint project between CMSA and Tsinghua University. There are many beautiful lectures that survey different developments in mathematics and allied fields. You can find them on YouTube, on the CMSA YouTube channel. And today we're very pleased to have Marc Lackenby from Oxford University, and he'll tell us about the complexity of knots.
Great. Well, thanks very much. It's a really great pleasure to be here and to be given this opportunity. So thanks very much. I should say that the aim of this talk is to be accessible, and so I encourage you to ask questions to stop me. That's completely fine. I gather that you can put questions in the Q&A. There's a special box to put it in, so please do that. Okay, so I'm going to be talking about knots, and knots, as we all know, are just simple closed curves smoothly embedded in 3 space. And you view 2 knots as equivalent or the same if one can be deformed to the other without passing through itself. So these here are the 3 simplest knots. There's the unknot, the trefoil, and the figure 8. And the sort of history of knot theory, after some initial work by Gauss, things really got started with the work of Tate in the 19th century, late 19th century. And he embarked on a project to tabulate knots. And the rationale for this is that they thought perhaps knots were the atoms, were knotted vortices in the ether, and that perhaps a tabulation of knots might go some way to explain properties, for example, in the periodic table. It turned out to be completely not the case, but nonetheless, the work that Tate did definitely had some value. This is, you can see here an excerpt of one of his tables, appeared in the Transactions of the Royal Society of Edinburgh, and it's the first 7 orders of knottiness. So knottiness is defined as follows. You consider a diagram of the knot, a projection to the plane, and you look at the number of crossings in that. And the minimum of that is the knottiness of the knot. We now call it the crossing number. And so they're quite extensive tables, and his tables were remarkably accurate. They were complete, and they didn't have duplicates. And the question that I want to ask is, how can we be sure about this? In other words, given 2 diagrams, how can we decide whether they represent the same knot? So Tate was aware of that this was an issue. It's not clear that he was aware that this was a mathematical question, but he was certainly aware that this was an issue. So this is the equivalence problem for knots. It's obviously fundamental to the subject. And interestingly, it was also raised by Alan Turing. So in his last published paper, Solvable and Unsolvable Problems, he discussed this particular question. He says, no systematic method is yet known by which one can tell whether 2 knots are the same. And you can see here an excerpt from that paper where he's drawn a trefoil knot, and then he says, in the figure below, he says is a possible representation of this knot as a number of segments joining points. And the idea is that that representation is machine readable. So you can input a knot into a computer in that format. And the idea is you put in 2 such knots, And you ideally want the computer to be able to answer the question, are they the same or not? And although he didn't say it explicitly, it's clear, you can see from the title of the paper, that he was at least raising the possibility that this might be an unsolvable problem, something that computers could never solve. And in fact, higher dimensional versions of that problem, you can talk about n spheres embedded in Rm for high dimensional m and n. That high dimensional version of problem is known to be unsolvable. But in classical knots, it turns out that it is solvable, and that's one of the things that I want to talk about today. So major progress on this was made by Haken, and I'll talk about his work in just a second. But there's an interesting special case, which is, can you even recognize the unknot, right? So the unknot is the round circle in the plane, or any knot that's equivalent to it. And it's not clear that if someone gives you a diagram and says, is that the unknot, that you can necessarily answer it. And this, for example, this diagram here, this is a diagram due to Goeritz. You look at that, it is in fact the unknot. You can deform this just to the round circle, but it's not clearly, obviously, that it's possible to do that. And actually, this particular diagram I'm going to discuss more in detail later. You can kind of do that one by eye, but this one, this is a diagram that due to Haken, which is in fact the unknot, and I defy anyone to be able to see that. So I think when you see these pictures, you realize that this is, potentially a very difficult problem. No obvious solution, but there is a solution. So in the early 60s, Wolfgang Haken gave an algorithm to decide whether a knot represents the unknot. And then he was able to solve, more generally, the equivalence problem for knots. There was one class of knots that he couldn't do, the so-called fibered knots. Those are ones whose complement admits a vibration over the circle. They were dealt with by Hemion in the late 1970s. And then this whole thing was written up properly, and various cases which hadn't been addressed were dealt with, or by Matveyev in the early 2000s. So now there is an algorithm to decide whether two knots are the same or not. And I'm initially going to focus on the case of the unknot. And the way that most ways of dealing with the unknot are by the following very elementary characterization. That a knot is the unknot if and only if it's the boundary of an embedded disk. And the way to see that is that if I start with the round circle, well, that obviously bounds a disk in the plane. If I then deform that unknot to deform it in 3 space, I can take the disk with it, and it still stays the boundary of an embedded disk. Conversely, if a knot bounds an embedded disk, you can slide the knot over that disk until it's nearly a round circle, and therefore manifestly unknotted. Okay, so we're going to use this characterization of the unknot. The other thing we do is use 3-manifold theory. So you typically view the knot, instead of living inside R3, you think about it living inside the 3-sphere, and you often drill out a little open regular neighborhood of the knot. And what's left is called the exterior of the knot, and it's a compact 3-manifold with toral boundary. Okay, so someone's given you a knot, you want to work out whether it's unknotted. In other words, you want to be able to say, does it bound an embedded disk? And the way that Haken approached this was he looked at the knot exterior and then he triangulated it. And that's a very straightforward thing to do. You can triangulate the knot exterior in a rather simple way, where the number of tetrahedra is a linear function of the number of crossings in your diagram. And then you look for spanning disks sitting inside that three-manifold. And it turns out that it's sufficient to look at a special type of spanning disk, namely those that are normal, right? So a surface properly embedded in a triangulated three-manifold is called normal if it intersects each tetrahedron in a collection of triangles, as shown, and squares. So normal surfaces had actually been introduced several decades before Haken's work by Kneser, and then they were taken up by Schubert, but Haken really developed the theory. And one of his insights was that it's actually a good idea to just encode a normal surface by a list of non-negative integers. And those integers just count the number of triangles and squares of each type. So that in each tetrahedron, there are 4 possible triangle types, just going adjacent to the 4 vertices, and there are 3 possible square types. And so you get a list of 7 t integers, where t is the number of tetrahedra. And it turns out that they satisfy various constraints. One of them is the matching equations. So if I have a face of my triangulation, which isn't on the boundary of the manifold, then it has 2 tetrahedra, one on each side. And a normal surface intersects that face in arcs. And there are 3 archetypes running close to the 3 vertices of the face. So here we're just focusing on just one of those archetypes. Well, those arcs, they come from triangles and squares on one side and triangles and squares on the other. And they have to patch up. And therefore, you get this linear equation. So you get one linear equation for each archetype in each face. And those are called the matching equations. There's another constraint called the compatibility conditions, which just assert that you don't have 2 different square types in the same tetrahedron. Because it turns out that if you have 2 different square types, they necessarily have to intersect, and you don't get an embedded surface. And Haken realized that there's actually a 1-1 correspondence between properly embedded normal surfaces and non-negative integer solutions to the matching equations satisfying the compatibility conditions. So, although it's not obviously a good thing to do, this is what Haken did do. He kind of translated questions about normal surfaces into what's not much more than linear algebra. And one basic tool from linear algebra you get is the notion of the sum of 2 surfaces. So we say that a normal surface S is a sum of 2 normal surfaces S1 and S2 if their vectors add in that way. And a surface is called fundamental if it's not a sum of other normal surfaces. So what Haken showed, and this isn't actually that hard, that if you have the exterior of the unknot triangulated in some way, well, we know that because it's the exterior of the unknot that it contains a spanning disk. But in fact, you can put that spanning disk in normal form. And moreover, you can arrange, and this is harder to show, you can arrange that it's actually fundamental. Moreover, you can construct all fundamental normal surfaces. It turns out that fundamental surfaces can't be too big in some sense, can't have too many triangles and squares. So you can actually construct them all. So the way that Haken's algorithm worked was as follows. Someone's given you a diagram and you need to work out whether it's the unknot. You triangulate the knot exterior. You find all fundamental normal surfaces. You go through each one in turn and you check whether it's a spanning disk. If it is, the knots, one of them is a spanning disk, the knot is the unknot. Otherwise, it's not. So that's Haken's algorithm, and it still remains important to this day. So now, though, there are many other ways to decide whether or not is the unknot. And here's a list of, I think, a complete list. You can use Haken's algorithm. You can look at the fundamental group of the knot complement. And you can, well, in general, you can create a presentation of that group. That's not so hard, but dealing with finitely presented groups is a difficult thing in general. But it turns out that it's useful to consider homomorphisms from that group to finite groups with non-cyclic image. And it turns out that, well, if your knot's a trivial knot, then its fundamental group, the fundamental group of its complement is just the integers. And so every image is cyclic. But if the knot is non-trivial, then it turns out that you always have some homomorphism to a finite group with non-cyclic image. That actually uses lots of interesting bits of maths. It was explored in detail by Kuperberg, but he used Kronheimer and Rüffler's work on representations to SU2 as an intermediate stepping stone. There are other methods. You can use so-called sutured manifold hierarchies, which are a tool developed by Gabai to construct taut foliations. And they be suggested by Ian Agol as a method of doing unknot recognition, and I picked up on that. Famously, Kofanov homology detects the unknot. So this was proved by Kronheimer and Rüffler. And so given your knot, you compute its Kofanov homology, and if it's the Kofanov homology of the unknot, then it turns out by their theorem that it has to be the unknot. Heegaard-Floer homology also detects the unknot. This was actually known since the very inception of Heegaard-Floer homology by Bosphart and Szabo. But what was less obvious was that Heegaard-Floer homology was computable, which you obviously need if you're going to turn it into an algorithm, and that was proved by Sarkar and Wang. There's also an approach using arc presentations. I'm not going to discuss those in detail here, but Dinikov's work on this was completely groundbreaking, and I'm going to mention some of his results later. So arc presentations are where you consider an open book decomposition of the three-sphere with binding circle, just a round circle, and then you might put your knot in a nice position with respect to that. It's an extremely powerful method with lots of nice applications. You can also use geometric structures. Obviously, this was pioneered by Thurston, and how they can be used to detect the unknot was explored in detail by Kuperberg. And then there's a rather elementary approach using Reidemeister moves, and this is actually what I want to discuss now. So it's a very foundational theorem in knot theory that any two diagrams of the same knot differ by a sequence of Reidemeister moves, as shown. And this has an algorithmic consequence. It implies that in the situation where two diagrams represent the same knot, you'll always be able to prove that to be the case, eventually. So suppose I have two diagrams of the same knot. Well, I know by Reidemeister's theorem that they differ by a sequence of Reidemeister moves. So I can take my first diagram. There are only finitely many Reidemeister moves that can be applied to that. So I get a collection of diagrams. To each of those, I apply all possible Reidemeister moves, and so on and so on. And you get this increasing collection of diagrams. And eventually, you'll hit the second diagram. And then you'll have proved that your two knots are the same. It's worth emphasizing that this does not give you an algorithm for solving the knot equivalence problem. Because if someone had given me two different knots, then this process would never terminate. And so actually knowing when to terminate is important in this area. And there are, if you look at, say, the analog of this for, say, group presentations, well, it's well known that if I have two finite presentations of the same group, then they differ by a sequence of Titze transformations. And so if they are the same group, then you'll always be able to prove that. But famously, it's not possible in general to decide whether two finitely presented groups are the same or not. And so not knowing when to stop your Titze transformations in that situation is a fundamental issue. So you can quantify this in the following theorem. It's a pretty elementary theorem, but I think it's illuminating. It says that there's an algorithm, the following are equivalent. There's an algorithm to decide whether any two knots are the same. That's the same as the existence of a computable function R in two variables, with the property that any two diagrams of a knot with C1 and C2 crossings differ by a sequence of Reidemeister moves with length at most R of C1 and C2. Okay, so to see this is not very hard, right? So let's just see why 2 implies 1. Suppose I have my computable function. Well, that gives me an a priori upper bound on the number of Reidemeister moves I need, given two diagrams. So if I've got two diagrams and I don't know whether they're the same knot or not, well, just like before, I can keep on applying Reidemeister moves to one of them, and eventually I'll either hit the other one if they're the same knot, or by the time I've done this many Reidemeister moves, R of C1, C2, I still haven't got the second diagram, and by this result, I know they're different. The converse is also not very hard. So suppose I have an algorithm to decide whether two knots are the same. How do I create this computable function R? Well, how would I compute R of C1, C2? Well, I would just enumerate all knot diagrams with C1 and C2 crossings. I would then take those knots and divide them into groups according to their knot type. And I can do that by the hypothesized algorithm. Then for each collection of knots, I know I've got them all of the same type. And so by Reidemeister's theorem, all of those diagrams differ by Reidemeister moves. And now I can just find those Reidemeister moves, just keep on trying. And that gives you a computer program then to find this bound on R of C1, C2. And that shows you that R is a computable function. So it's a pretty trivial theorem, but it shows you the importance of bounding the number of Reidemeister moves. As I said before, by work of Haken and Hemion and Matveyev, we know now that there is an algorithm to decide whether two knots are the same. So we do know there is this computable function R, but obviously we'd like to get R as small as possible, and that would lead to more efficient algorithms. Okay, so what's known about Reidemeister moves for the unknot? Well, for a long time, this was the best upper bound due to Haas and Ligarius. It says that if I've got a diagram of the unknot with C crossings, it can be converted to the trivial diagram with no crossings using at most exponentially many Reidemeister moves. So how does that work? Well, it uses Haken's result. So you first of all, you take your diagram, you use that to triangulate the knot exterior. Then by Haken's work, we know that it has a normal spanning disk, and that's fundamental. And then by this theorem that you've got in front of us, fundamental normal surfaces, they have an exponential bound on the number of triangles and squares. And so then what you do is you just slide the knot over this disk. And you look down and see as you slide your knot, the knot diagram gradually changes. and it changes by bounded numbers of Reidemeister moves at each stage. And so you get this exponential upper bound on the number of Reidemeister moves. So that's a computable function. So we see again that unknot recognition is algorithmically solvable, but it's a pretty big bound. And although we're going to see later much bigger numbers, but there seemed to be no good reason why it shouldn't be improved. However, it's worth saying that you can't improve that exponential bound by an improvement by finding a smaller spanning disk. So it turns out that there's a theorem due to Haas, Snowyink, and Thurston that says that exponentially large spanning disks might be required. So the way that works, so the theorem says that there exist unknots consisting of linearly many straight arcs, 10n plus 9. They're unknots, so they bound piecewise linear spanning disks, but the number of triangles in such a disk has to grow exponentially. So here you can see the diagrams that they created. They're pretty simple. What you do is you focus mostly on a braid capped off at the top and the bottom, and the braid consists of sigma 1, sigma 2 inverse, sigma 1, sigma 2 inverse, etc., and then the reverse of that. So they all just cancel each other out in terms sort of algebraically, and so you just get an unknot. But this braiding forces your spanning disks to get exponentially complicated, and that's what they proved. Nonetheless, it turns out that you can get a much better bound on Reidemeister moves. In fact, you can see just in these examples, I can undo this braiding using, in this case, most linearly many Reidemeister moves. So although these knots have large spanning disks, they're still not complicated in terms of the number of Reidemeister moves. Okay, so we actually now have much better bounds. I mentioned Dinokov's work before. One of the applications of Dinokov's work is the following remarkable theorem, that if you have any diagram for the unknot with C crossings, then you can convert it to the trivial diagram. Now, his theorem doesn't bound the number of Reidemeister moves, but it bounds the complexity of the intermediate diagrams. He showed you don't need to go via diagrams which are more than quadratically complicated. In other words, have more than 4 C plus 1 squared crossings. So that's an upper bound on the intermediate complexity of these diagrams. It doesn't bound the number of Reidemeister moves. I gave a polynomial upper bound on that. That you can convert any diagram for the unknot with C crossings to the trivial diagram using at most 236 C to the power 11 Reidemeister moves. It's still quite a big number, but it is a polynomial, and that represents quite a significant improvement over what Haas and Lagarius did before. The proof blended these two approaches to analyzing the unknot. Haken's work on one hand, but also Dinokov's work using ARC presentations. I don't have time to describe it here. It was quite a complicated proof. It also used some ideas from dynamical systems as well. That's upper bounds of Reidemeister moves. What about lower bounds? Well, you always have a linear lower bound on the number of Reidemeister moves you need. If I've got a diagram with C crossings, the unknot, say, but each Reidemeister move changes the number of crossings by at most 2. So the number of Reidemeister moves that I need to trivialize it is at least C/2. But actually, results due to Haas and Nowick prove that actually sometimes you need more than that. That they gave diagrams of the unknot with linearly many crossings, but that need quadratically many Reidemeister moves to turn them into the trivial diagram. So now the situation for the unknot is quite satisfactory. Polynomial upper and lower bounds of Reidemeister moves. They don't have the same degree, and so it's not clear exactly where the truth of that lies. It's certainly the case that you can improve my 11 degree down to 10, but I don't know how to do any better than that. So we still don't know that, but still, nonetheless, we have a good estimate now for the number of Reidemeister moves for the unknot. What about general knots? Well, here things start getting pretty bad pretty quickly. And here's the following kind of remarkable, even slightly comic theorem gives the best known upper bound on Reidemeister moves for general knots. It says the following: that if you have two diagrams, D1 and D2, for the same knot, and they have C1 and C2 crossings, then we know they differ by a sequence of Reidemeister moves. But how many? Well, I haven't written it in yet. I've just left a really big space. And the reason I left a really big space is because it's a really big number. The number of moves is at most 2 to the 2 to the 2 to the 2 to the, and the very top of that tower of 2s is C1 plus C2. How high is that tower of 2s? It's exponentially high. It's k to the C1 plus C2 high. And what's k? Well, it's a mere 10 to the 1 million. Okay, so that's crazy. But that is the best, remains the best known upper bound for general knots. So clearly that's not the truth of the matter. The truth of the matter should we be able to do much, much better than that. But it sort of highlights the general theme, actually, that although knots are tractable objects, they're not tractable in any straightforward way. And this is a concrete example of that. Now, I've been working on improving that. I can't improve that for general knots, but what I can do is the following. If I fix my knot type, okay, so say look at just trefoil knots or figure-8 knots, then there's a polynomial, P, that depends on that knot type. So that if I have any two diagrams of the knot with C1 and C2 crossings, then they differ by at most P applied to C1 plus P applied to C2 Reidemeister moves. So if you're willing to fix the knot type, then like the unknot, you get a polynomial bound on Reidemeister moves. And so that's, I feel, is pretty substantial progress compared with this general upper bound above. It's worth saying, though, that these polynomials, they're not small polynomials, right? So for the figure-8 knot, the polynomial pk has degree 531,468. So that's a pretty big polynomial. And that actually, I think, is a pretty interesting point that we're going to be coming on to complexity theory later, but in general, you know, for example, if you're, say, looking at algorithms, you say if an algorithm can be completed in polynomial time, it can be done fast. Well, you might hope that if you have a polynomial bound on Reidemeister moves, that's an efficient bound. But you can see here that these polynomials can get really, really big. And so that's of considerable interest to try to improve these bounds. I'll mention very briefly how this new theorem is proved. I've been finishing writing it up this summer. It'll be coming out in the next couple of months. Okay, so how do you deal with general knots, right? So the unknot, there was this nice characterization of them. They're the ones that bound embedded disks. But for general knots, you don't have that. And instead, what you should use is hierarchies. So hierarchies were invented by Haken in his solution to the equivalence problem for knots. So what is a hierarchy? Well, you start with your three manifold, which is the exterior of your knot. And instead of finding a spanning disk, you find some surface sitting inside there. It needs to be properly embedded, and it needs to be, it turns out, what's called incompressible, which means it can't be simplified to a surface of smaller genus. And it also needs to be orientable. And then you cut along that surface. You cut actually along a little open regular neighborhood of that surface. And the result is a new three manifold called that M2. Then you cut along, you find a surface in there, and you cut along that, and so on and so on. And it turns out that you can arrange that you end in just your final manifold just being a collection of balls. And this is a hierarchy. So let me kind of give you an example of this. This here on the top left is the knot 5-1. And the first surface in the hierarchy that I'm going to use is it's going to be a spanning surface for the knot. It's shown in gray here. And when you have a little crossing, the surface just has a little half twist in it, as you can see. So that actually turns out to be an incompressible surface, properly embedded, orientable, and then you cut along it. And what's the three manifolds? What is the three manifold that is left? Well, we're cutting on a little open regular neighborhood of that surface. So imagine thickening up that surface. Then what you get when you thicken it up is this picture on the bottom left here. So the outside of that, which is just a handle body, is the next surface, M2, the next manifold, M2. And then you can just find two disks properly embedded in there, you cut along them, and then the result is a three ball, and that means you're done. So that's a hierarchy for this knot 5-1. So how did Haken use hierarchies? Well, a hierarchy specifies a cell structure for the exterior of the knot. Best not to think about the three cells just yet. What's the two skeleton? Well, the two skeleton is the union of the boundary of the manifold, the toral boundary, together with all of the surfaces in the hierarchy. So where a surface runs over a bit of boundary, you get a sort of junction which forms a one cell. Say I have a bit of surface and I have a later surface running over it and maybe another surface running over that. Where those surfaces intersect at a point, you get a zero cell and so on. And we've arranged that the complement of the hierarchy is just balls. And so you take those to be three cells. So given a hierarchy, there's a sort of canonical cell structure for the knot exterior. And then what Haken does, or what MatVF does, is you then subdivide this to a triangulation, which in some sense is canonical. You can just sort of cone off, subdivide the two cells into triangles, coding from a central point, subdivide the balls into tetrahedra and so on. And so what you get is this triangulation for the knot exterior, which in some sense is canonical. It just depends on this choice of hierarchy. So the way that, in outline, the way his algorithm worked, and the details are fiendishly complicated. When MatVF wrote them up, they spanned several hundred pages. But in overview, the way it works is as follows. You're given two diagrams, K1 and K2, for knots. And you want to work out, are they the same or not? Well, you build these canonical triangulations for these two knot exteriors. Don't really rely on any choices. They rely on a choice of hierarchy, but you can sort of remove that choice. And so then, if the two knots are the same, they'll have the same canonical triangulations. And so you can just check that. You can just check whether two triangulations are combinatorially the same. And so if they are, then you know that the knots are the same. But if they're not, then you know the knots are different. And so that's the way the algorithm worked. And so you can see that because you're dealing with hierarchies, the first surface in your hierarchy, say someone's given me a triangulation for my knot exterior, I need to control the first surface in my hierarchy. Well, it turns out that you can in general make it fundamental. That might mean it's exponentially complicated. So when I cut along it, forming M2, it might have then exponentially many tetrahedra. And so my next surface might be even more complicated, and so on and so forth. And it's for that reason you get these towers of exponentials coming up in your arguments. It's because of hierarchies that you get towers of exponentials, and the height of the tower is the length of the hierarchy. So my polynomial bound on Reidemeister moves for a fixed knot type also uses hierarchies, but it also blends together normal surface theory as well as Dinokov's methods. So it's definitely a combination of many different techniques. It's what makes the proof quite long and quite complicated. Okay, so that's general knots. So far, I've mostly been focusing on Reidemeister moves. And I think that's a reasonable thing to do. We've seen that a computable upper bound on Reidemeister moves is equivalent to the solution to the equivalence problem. And for example, for the unknot, we have a polynomial upper bound on Reidemeister moves. But as I also said before, Reidemeister moves are not the only way to solve the equivalence problem, and not the only way to solve the problem of deciding whether something's the unknot. There are many other ways. And so really, actually, it's very natural to then ask, what is the computational complexity of these problems? In other words, what are the fastest possible algorithms that you could use? So here's a sort of survey of what's known. The big unsolved problem in this area, and I view this as one of the main problems, unsolved problems in knot theory, is there a polynomial time algorithm to decide whether a knot diagram represents the unknot? So we have a polynomial upper bound on Reidemeister moves. But that doesn't give you a polynomial time algorithm. It gives you an exponential time algorithm. Because to decide whether something is the unknot, I would have to consider all possible sequences of given a diagram, I'd have to consider all possible sequences of Reidemeister moves of that length. Even with a polynomial bound on length, you're still going to have to go through exponentially many diagrams. So is there a polynomial time algorithm? None of the techniques that we have are getting close to that, with the exception of one, which I want to talk about a little bit later. However, there are still interesting things that you can say about the computational complexity of unknot recognition. And the first result in this direction was due to Haas, Lagarius, and Pippinger, who proved that unknot recognition lies in NP. In other words, if a knot is trivial, there's an efficient way of certifying that it's trivial. So their certificate is as follows. Someone's given you a knot, and you need to prove that it's the unknot. How do they do it? Well, they say, here's the triangulation for the knot exterior, and here is a spanning disk, which is normal and fundamental. They make it slightly stronger than fundamental. And then from that, they can then say, and this is a spanning disk. Now, actually showing that the normal surface is a spanning disk is not straightforward, and that's why this is a serious theorem. There's now an alternative, much simpler certificate, just using my result on Reidemeister moves. Someone's given you a knot diagram. How can I certify that it's the unknot? Well, I can just give you a sequence of Reidemeister moves, taking it to the trivial diagram. And because we have this polynomial bound on Reidemeister moves, that certificate is only polynomially long and can be checked, therefore, easily in polynomial time, whether it really does work. And so that shows you a very simple certificate then, or a simple way of showing that unknot recognition lies inside NP. Here's a remarkable theorem due to Kuperberg that unknot recognition also lies in co-NP, assuming the generalized Riemann hypothesis. So co-NP means that if someone gives you a knot and it's non-trivial, then you can certify that in polynomial time. So the way he did that was he said, right, well, the certificate for non-triviality is a homomorphism to a finite group with non-cyclic image. So it was already been known as that there was such a homomorphism to a finite group with non-cyclic image. That used it. It used work of Kronheimer and Rifka on representations of SU2. Or more generally, once you have a linear representation, you then get homomorphisms to finite groups as well, just because linear groups are residually finite. But we need to get a homomorphism to a finite group with non-cyclic image that's relatively small, so that I can write down the group, write down the homomorphism, and check in polynomial time that I really do have non-cyclic image. So to get homomorphisms to finite groups whose images are not too big, that's where the generalized Riemann hypothesis comes in. And it's a remarkable argument. I, however, removed GRH, unconditionally showed that unknot recognition lies inside co-NP. I used quite different techniques. They were inspired by work of Agol, suggestions of Agol, which used these so-called sutured manifold hierarchies to certify that the knot is non-trivial. That said, though, Kuperberg's work is still extremely important, and in fact, the generalized Riemann hypothesis is assumed in various other recognition algorithms in three-manifold theory. For example, recognizing the three-sphere. It's worth saying that it's a standard conjecture in complexity theory that no problem that is in NP and co-NP is NP complete. And so it seemed, I mean, if there was just a single problem in NP intersect co-NP that it was NP complete, that would mean that you'd get collapse, and it would be it would have ramifications for complexity theory, major ramifications for complexity theory, and most people think that's not the case. So this means that probably unknot recognition is not NP complete. Problems that are in NP and co-NP are good candidates for things that could be solved in polynomial time. So although it's not conclusive evidence, it's reasonable to hope that there might be a polynomial solution. In recent work, I actually showed that there's a quasi-polynomial time solution. So that means that you can recognize the unknot. In this amount of time, it's 2 to the log c to the k. So c is the crossing number of your given diagram, and k is some constant, which is actually 3. So if k was 1, you'd have 2 to the log c, and so you'd end up with like a polynomial function of c. And because there'd be constants as well out the front. But once k is bigger than 1, then you have what's called quasi-polynomial time. Again, I don't have time to discuss that here, but it uses hierarchies as well. What about general knots? Well, for consequence of my polynomial upper bound or Reidemeister moves for each knot type is that for each knot type, the problem of deciding whether a knot has that type is in NP. So, for example, is a knot a trefoil? Is in NP. Is a knot a figure 8? It's in NP. And the certificate is just a polynomially bounded sequence of Reidemeister moves, taking your given diagram to some fixed diagram. So that's a nice algorithmic consequence of my polynomial bound. What's known generally, though, the best known upper bound is due to Cooper-Berg, but the problem of deciding whether 2 knot diagrams with C1 and C2 crossings, a slight typo there, deciding whether they're equivalent, the running time for that is at most 2 to the 2 to the C1 plus C2. But unlike previously, that tower of 2s has fixed height, probably height 5. His proof, he doesn't specifically give you the height, but it seems that one can compute the height of that, and it's probably 5. He actually used hyperbolic structures, in fact, so I'll talk a little bit about them shortly. So that's where we're at. You can see that there's quite a lot known, particularly for the unknot, although the main problem of detecting the unknot, whether it's in polynomial time, remains unresolved. For general knots, it's really bad. These towers of 2s are they're hard work to prove, but they're clearly not good upper bounds on the running time. But there's this glimmer of hope with this fact that recognizing a fixed knot type is an NP. And if I had to stick my neck out, I would conjecture that actually the general knot equivalence problem is in NP. So I mentioned that Cooper-Berg's work used hyperbolic structures. So much of the other work that I've discussed so far doesn't. But hyperbolic structures really do arise naturally. And in fact, hyperbolic structures are, in practice, one of the best ways of deciding whether 2 knots are equivalent. So a hyperbolic structure is just a Riemannian metric on the 3-manifold that's complete and locally isometric to hyperbolic 3 space. It turns out that when you have such a thing, that's exactly the quotient of hyperbolic 3 space by a discrete group of isometries acting freely. And Mostow's rigidity theorem says that if a 3-manifold, or more generally an n-manifold with n at least 3, has a finite volume hyperbolic structure, then that is unique up to isometry. And largely due to work at Thurston and then Perelman, hyperbolic structures have become central in 3-manifold theory. And one of the main things that Thurston proved was the so-called monster theorem that gives hyperbolic structures on knot complements. The theorem is that the complement of a knot in the 3 sphere has a finite volume hyperbolic structure if and only if the following all hold. It's not the unknot. It's not a torus knot. So torus knots are knots that can be drawn on the standardly embedded torus in 3 space. And it's not a satellite knot. So satellite knots are as shown here. A satellite knot, you take a non-trivial knot, in this case a trefoil, you thicken it up to form a solid torus, and then you put your satellite knot in that solid torus. And as long as it's not a core curve of the solid torus or doesn't lie inside a 3 ball inside that solid torus, it's called a satellite knot. And so Thurston proved this. And by Mostow, such a structure, hyperbolic structure, is unique. And so that means that geometric invariants, such as the volume or the length of the shortest geodesic, they're all actually topological invariants of the knot. And this is actually useful in terms of deciding whether 2 knots are the same via the so-called Epstein-Penner decomposition. So any non-compact finite volume hyperbolic 3 manifold has a decomposition into ideal polyhedra. So hyperbolic 3 space is, in this Poincare model, is the open unit ball with this negatively curved metric on it. And if I take a collection of points in the interior of that ball and take their convex hull, that's a polyhedron, hyperbolic polyhedron. But an ideal polyhedron is when I take a convex hull of points on the spheroid infinity. And famously, Thurston showed that the figure 8 knot can be expressed as the union of 2, it's the figure 8 knot complement can be expressed as the union of 2 hyperbolic regular ideal tetrahedra with their faces identified in pairs. And in fact, this is a very general construction. Every non-compact finite volume can be built in this way. And in fact, the construction can be made canonical. This is the real strength of Epstein and Penner's construction. In other words, if 2 people were to be given the same hyperbolic manifold, they could make sure that they had the same decomposition into ideal polyhedra. So the consequence of this is that 2 finite volume hyperbolic 3 manifolds, they're homeomorphic if and only if their Epstein-Penner decompositions are combinatorially isomorphic. So I can solve the equivalence problem if I've got my hyperbolic manifolds by computing the Epstein-Penner decomposition. It's just polyhedral decomposition, and asking, are they actually same polyhedral? Do they have the same polyhedral decompositions or not? And this is actually done in practice. So there's this amazing program, SNAP-E. It was created by Jeff Weeks and then developed by several people, Dunfield and Culler. They changed the name to SNAP-E with a Y when they introduced it into Python. And it's an incredibly powerful tool. So you can just take your knot, you can input a diagram for it using your mouse. This is a picture of the figure 8 knot. And then SNAP-E will attempt to find a hyperbolic structure on its complement. And you can make it use exact arithmetic, so where you're solving equations using exact arithmetic. So numbers are not given as floating point numbers, but as roots of polynomial equations with little intervals about them specifying the root. And because you do exact arithmetic, there's no worry about round-off error. So if SNAP-E finds a verified hyperbolic structure, then that definitely exists. And SNAP-E can compute many useful geometric quantities. So, for example, like this is something I did. You spits out this Dirichlet domain for this knot complement. So this is the figure 8 knot. It has a hyperbolic structure, and there's the different Dirichlet domain that it spits out. You can see it sort of rotating around there. It'll also decide whether two knots are the same. So you put your diagrams into Snappy, or you encode them by means of a triangulation, say. Find the hyperbolic structures on those knots, hopefully, not always, but if it does, you know you really have the hyperbolic structure. It'll compute the Epstein-Penn decomposition, and it can then from that decide whether or not the knots are the same. So if that process works, then the answer is correct. But unfortunately, it's not an algorithm because it's not guaranteed to work. And so, but understanding why Snappy seems to work so well seems to be, it seems to suggest that really hyperbolic structures really are a useful way of analyzing the knot equivalence problem. So in my view, they're one of the most promising ways of finding provably efficient algorithms to decide whether two knots are equivalent. And as I said, Kuperberg used them to find what's the best known upper bound for solving the equivalence problem for knots. Okay, so let me just close now by talking about some of the there are lots of problems in this subject. There's a lot that we don't know. But here are what I consider to be some of the really interesting ones. I mentioned this before. Is there a polynomial time algorithm to recognize the unknot? That I view as quite central. Well, generally, what's the computational complexity of the equivalence problem for knots? You can also ask the same question more generally, the homeomorphism problem for three manifolds. And so here our knowledge is really, really bad. So best upper bounds on these computational complexity is due to Kuperberg, Tower of Twos. The best lower bounds, well, for knots, we don't have any good non-trivial lower bounds. For general three manifolds, there's good evidence that it can't be done in polynomial time because it's at least as hard as the graph isomorphism problem. And that's probably, there's good evidence that that can't be solved in polynomial time. But those upper and lower bounds are a million miles from one another. And so I view this as pretty central in we need to get these bounds closer. Reidemeister moves. I spent a lot of time talking about that. We need to get better upper bounds on Reidemeister moves for general knots. Because if you fix your knot type, we have polynomial bounds. If you vary your knot type, one should be able to get much better answers than what we've got so far. And what about lower bounds? In general, we just have a quadratic lower bound on Reidemeister moves. Is that the truth? Or might one be able to get even bigger lower bounds? As I mentioned, I think hyperbolic structures are a particularly promising way forward. But what is the computational complexity of finding a hyperbolic structure if it exists? This is not, I mean, you can find upper bounds, but they're not very good. That's one of the sort of key methods that Kuperberg used. In practice, it seems that finding a hyperbolic structure can be done efficiently. So there's quite some positive evidence for this final problem, which is hyperbolicity in NP. In other words, if a knot is hyperbolic, can one certify its hyperbolicity in polynomial time? And even better, can one find the hyperbolic structure? But that's just the decision problem. Is this not hyperbolic? That seems a really good question. Is it in NP? So that's a sort of a survey of where we're at. Progress is constantly being made in this area. Knots are tractable objects. but only just. And so there's still an awful lot that we don't know. Okay, I'll leave it there. Thank you very much.
Thank you, Mark, for a beautiful, beautiful talk. We have plenty of time for questions. If people want to ask questions, raise your hand, and I think I can unmute you and you can ask a question. Or you can type it into the Q&A. Well, in the meantime, I'll ask. So your new result, you say that there's a polynomial that bounds how many Reidemeister moves you need to, if you fix a knot type. Is there a bound on the degree of that polynomial?
Good question. So yes, so I gave for the figure 8 knot this right. Crazy, like in the hundreds of thousands.
Yeah.
It turns out that the degree depends only on the length of a hierarchy. Now, the hierarchy has to have certain properties. And actually, for the figure 8 knot, the hierarchy that you have to use has length 5, which means you have to cut along 5 surfaces 5 times until you end up with balls for the type of hierarchy we need. And that's what makes that number big. This might be a good way, it's plausible at least that there might be a universal bound on the length of the hierarchy, and that would then give you a universal bound on the degree, and then it seems then plausible that one might be able to then get a polynomial that works for all knots. And if you had that, then the general knot equivalence problem would be in NP.
I was wondering.
So that's a pretty promising line of inquiry. I spent quite a long time thinking about it, and I haven't been able to do it, but I don't think it's hopeless.
Good.
Right. I have a question in front of me.
You do, good. Okay.
Okay, so it says, assuming a knot hyperbolic, is the complexity of the knot type recognition problem known, for example, using the ideal triangulation decomposition explained? So yes, so there are 2 aspects to that. There's one thing, there's knowing it's hyperbolic, and there's another thing, actually having the hyperbolic structure. So if I actually have the hyperbolic structure, then it's actually a very efficient algorithm for me. In what sense? Maybe as say ideal tetrahedra with their bases glued in pairs. So if you actually have the hyperbolic structure, then you can solve the equivalence problem quickly, in the sense that given 2 such representations, I can decide whether they are the same knot or not. The difficulty seems to be finding the hyperbolic structure. That's the bit that we don't know. We know, and it kind of makes sense, right? Because Thurston's theorem, which gives you the hyperbolic structure, is really complicated. You know, the proof is thousands of pages long, and it's in the end non-constructive. It doesn't give you the hyperbolic structure; it just proves that it exists. Right. So that means that if someone had just given you a triangulation and someone had said this is a hyperbolic manifold, relating that triangulation to the hyperbolic structure seems to be, I mean, one can do it, but it's hard work, and that's the source of the complication.
Okay. Any other questions? Well, if not, let's thank Mark again. Thank you. And we'll be announcing future lectures in the series soon. So look for those. Thanks again.
Thank you very much indeed.